Hello, wonderful people. Welcome to Cosmology Talks and Cosmology from Home. This is the last of the Dark Energy Survey Supernovae talks, for now. But it's also probably the funnest. In this one, we're not hearing about new constraints or evidence for new physics or whole new observables. Although if you want any of that cool stuff, you should definitely check out the other recent talks. Instead, in this one, the speakers are challenging perhaps the central dogma of cosmology. Is the universe really expanding? The speakers are Ryan White, who's a student in Queensland, and the now familiar Professor Tamara Davis, also from Queensland. The spoiler for this talk is yes. Yes, it is really expanding. But the proof here is really neat and also very clear, which is especially cool. The best evidence that the universe is expanding probably lies in the cosmic microwave background, not supernovae. There's just so much information that has been extracted from the CMB that could only possibly make sense if the universe is expanding. However, getting to the point where one understands why the CMB is such strong proof does take a bit of effort, and unless one sits down and puts in that effort, it can appear quite opaque. Ryan and Tamara instead take this awesome supernova catalogue and say, okay, look, if the universe is expanding and the supernovae are moving away from us, then as well as being redshifted, the light signal travelling to us should also be stretched in time. The simplest way to understand this is that in a frame where the distant supernova is moving with respect to us, the light emitted at the end of the supernova's time supernovaing was actually emitted slightly further away from us. So it has to travel a slightly longer distance to get to us, and therefore it should also take slightly longer to get to us. What this means is that if, as far as the supernova is concerned, it supernovaed for, let's say, 10 days, we should see it supernovaing for slightly longer than that. In other words, we should see a time dilation effect. And the more something is redshifted, the faster away from us it's moving, the greater the time dilation effect should be. This time dilation effect has been known about for ages and is actually corrected for in all supernova analyses. However, what's new in this result is the precision with which Ryan, Tamara, and colleagues at the Dark Energy Survey have measured exactly how it scales with redshift. And when compared to the prediction of an expanding universe, it matches very, very closely with an accuracy of 0.5%. So there are no anomalies or tensions here. ΛCDM might be on shaky legs, but the expanding universe most definitely is not. But that's enough from me. Let's find out what exactly you expect from the expanding universe and how Ryan and Tamara have measured it and what the results are. Welcome, Ryan and Tamara. Do you want to start by telling us briefly about your paper?
This is a really interesting and quite a short paper, I think, where we set out to find a detection of cosmological time dilation in the Type 1a supernova light curves with the Dark Energy Survey. DES is really important because it has a hell of a lot of supernovae and a very high redshift. And we expect that cosmological time dilation is more significant the further things are away. So it's really important that we have lots of supernovae at really high redshift. And essentially, the TLDR of the paper is that we look for light curves broadening in time. That is like the brightness over time of supernova light curves. They get wider at high redshift.
So since I was a kid, one of the first things that I got excited about when I heard about relativity and the fact that time can warp and space can bend, etc., was this idea that time doesn't run the same for everybody and that you have this time dilation effect. So the ability to actually go and measure it in the universe, I think, is pretty cool. I think like some of the motivation here is if the universe is really expanding, then and our redshifts are due to velocities of things away from us, then we expect that those things should also have time dilation. And it gets time dilated by a factor of 1 plus the redshift. Now, I really don't think that too many people doubt that the universe is actually expanding, but we do still get that question, and people have things. Even last year, I was getting people talking about a theory of tired light, where redshifts aren't actually due to expansion; they're due to some sort of loss of energy for some other reason. So it's good to just sort of like put in one of these foundations of our cosmological model, and confirm once again that yes, our universe is expanding, and also just to measure this really cool effect of time dilation, and put any question of that to bed once and for all. And time dilation is something that surprisingly hasn't been measured that well before. We did some, other people did some stuff with some of the first supernova measurements looked that the light curves at high redshift were wider than the ones nearby. And recently, some people have also looked at like quasar variability and whether that variability has sort of a longer tick at higher distances than nearby ones. But there's very few really good clocks out there that can act like the supernovae do as just a sort of a nice, precise single object clock that we can use to measure time dilation. And so with this sample, which has more distant supernovae than we've ever had before, we can make this measurement really nicely.
And I guess just in case we've got some very, very general audience, very skeptical people watching this, when Tamara says time dilation hasn't been measured very well, you mean cosmological time dilation, like the special relativity on Earth on fast-moving objects has definitely been measured very well and to high precision with, I guess, especially GPS satellites and things like that. But
if I use my blue dot to get somewhere, I've used time dilation because the GPS satellites are moving fast and in a different gravitational field to us. So yes, that's been measured very precisely here on Earth. We just haven't measured it that well. We have measured it, but just not really, really well for the expansion of the universe before.
Doing this is only really possible with the amount, like the sheer number of supernova light curves we have and how kind of precise they are with the dark energy survey. So with DES, we've got roughly 1,500 observations of individual supernovae, each with a light curve, usually in several different bands. So by bands, it's like filters with the telescope. We're looking at each supernova in a different color. And so what a supernova light curve looks like is essentially this plot here. So you can see that it starts out pretty dim. Over a period of a couple of weeks, it actually gets quite bright, and then it starts to fall off again. And the actual profile of this light curve changes with the color that you're looking at the supernova with. So it initially starts out quite blue, and over time, the type 1a supernova will get progressively redder. And you can see that here comparing the R, I, and Z bands. So these get progressively redder. And you can see that the Z band especially peaks at a late time. Sorry, it doesn't peak, but it gets higher than the other bluer bands at a later time, which means that the supernova is getting redder.
This y-axis says normalized flux. I guess it's not the case that the R band, I band, and Z band are all identical right at the beginning. It's just that this has been normalized such that they're identical at the beginning.
Exactly, yeah. Normalized to its peak brightness in that color band, yeah. Yeah, light curves do change quite a lot compared to color and also redshift. So this is a really good plot that I think Tamara actually made in a different paper. And it's essentially looking at all the DES light curves across all the different DES bands. So you have like a column for each of the G, R, I, and Z. And if you go left to right, you get to progressively redder bands that we're looking at these supernovae in. The x-axis is time, like before. The y-axis here is kind of the brightness of the supernova, but each light curve is offset by its redshift as well. So as you're going up, you're looking at supernova light curves at a larger redshift, at a further away distance, essentially. So you can see that if you look near the bottom, you're looking at all supernovae at the same redshift, more or less. And you can see that as you get redder, their shape changes quite a lot. And if you look at one single band, so maybe the I or the Z band especially, so the two rightmost columns, you can see that as you go up to a further redshift, that the shape also changes. And the reason for that is that when you look at a supernova in a further away redshift, you're looking at essentially intrinsically bluer light. Because we're looking at it in the same photometric band, as you get to a higher redshift, you're looking at intrinsically bluer light that's been redshifted into that red color that we see.
And an important thing to note about this particular plot, which I made, is that these have all assumed that the light curves are time dilated and gotten rid of the time dilation. So it's redshifted them back to how wide they would be if they were at redshift of 0. So that's been assumed in this particular plot.
Right, so anyone trying to pick out the effect by eye won't see it because it's been removed.
If we look at it without correcting for that assumed time dilation, we see essentially this. And now you can see that as you go further up, light curves are actually getting intrinsically wider as well, or extrinsically wider, I guess. So if you look high up on the y-axis for the Z band plot here, you're essentially seeing the same kind of shape that you'd expect very low down in the G or the R bands. And you can see that they are quite a bit wider in time.
If you flick between these two a little bit, you can see that Down at low redshift, they don't get much wider, but up at high redshift, they do get quite a bit wider. And so visually, that's what we're seeing. If you don't de-redshift, then you get the light curves being wider up at the top of this plot than at the bottom. But there's like weird peculiarities because if on just considering the right hand column, you can see that the really red light has the double bump, or you have at the very bottom, sorry, you have this double bump effect, which makes that look wide in that particular color. But when you go up to the very top, you don't get that double bump anymore. So you're actually the top of the red column should be compared to the bottom of the green column because those are the light curves that are in the same color.
Same color when they were like emitted by the supernovae, before they got redshifted by expansion.
They're like rest frame color.
It's the same part of the supernova spectrum.
Okay, so with that in mind, if we actually want to get the numbers of time dilation here, rather than just by eye seeing that they get wider, if we actually want the numbers, one really interesting thing we can do is we can pick out individual light curves that should have intrinsically the same shape. Yeah, so what we can do is we can pick out light curves from different colors, from different redshifts, that should have intrinsically the same shape and intrinsically the same color in the supernova's rest frame. This is probably one of my favorite plots in the paper. If you look at all the black dots here in the middle of the plot, those are the redshifts of each individual type 1a supernova. So where these black dots cross the colored bands, we can take those supernova light curves and kind of stack them all together. And so when we do that, we get essentially this. So these all, as I said before, are kind of the same intrinsic shape, and I hope you'll agree with me when you look at this. And they follow kind of like a homogeneous profile. So here the orange dots correspond to the R band data, which is roughly at redshift 0.2, the red for the I band at roughly redshift 0.5, and the purple for the Z band at roughly redshift 0.75. And I hope you'll agree with me as well that there's actually a problem with this. The colors don't line up with each other exactly. So I've gone and told you that these should be all intrinsically the same, but we can see that there's some gradient in color when we look at these stacked light curves.
Yeah, what does normalized flux mean?
So the normalized flux here is essentially the brightness of the supernova that we see, normalized to 1, to what we kind of expect the brightness to be from a model of the supernova light curve. So this is actually one of the only times in the paper that we use models of light curves rather than just the data.
I guess that's a little bit opaque, not knowing the models. So you saying it's suspicious that the yellow, red, and purple don't lie on top of each other. As a super naive, not knowing the model person, like it looks like if you just shifted the yellow dots up a bit and the purple dots down a bit, they would lie on top of each other. So maybe your model is just not normalizing the y-axis correctly, would be my naive outsider first comment.
That's a really good point. And if you look at the peak brightness especially, so on the x-axis that corresponds to the 0 point, you can see that the dots actually do line up pretty well. So their peak brightnesses are all lined up. It's only when you get away from the peak that those brightnesses essentially don't line up. But maybe it's not so much that the brightness isn't lined up, but maybe the time isn't lined up.
And we could dispense with the model completely if we just like took like the average of all of the data points near peak or something like that. But it's just a bit messier. So that would add some noise. So the model's not very important at all. It's just, getting that all of the things at time 0 to be about the same height.
Yeah, which I agree they are. So that previous naive objection is wrong.
So one of the key things that I propose in the paper is that if we actually want to find time dilation, one way that we can do that is scaling all of these points in time until they best fit vertically. So that is like, if we minimize the vertical flux scatter at each point, that's essentially equivalent to finding some signature of time dilation. So one way that we can do that, we need to scale all of these points by kind of like a similar function. And if we scale them all by 1 plus z to the power of b, where b is some free parameter, we can change that b until all of these dots best line up. So here's an example of where we've done that. We've essentially, with the code, just fit b until that vertical dispersion in the flux at every time is minimized. And you can see that when we do that, they all do line up actually quite well. And you get a very homogeneous shape.
When you say vertical dispersion, do you mean like between the average of the purple and the average in the red and the average of the yellow at each time?
Yeah, so all of them at once, essentially. So looking at all the points across every time, and we want to minimize how scattered they are vertically.
Like, will it rescale all the yellow points by exactly the same? I mean, you're saying Z approximately 0.21, but do you have actually more precise Z values for each yellow point?
Yeah, absolutely. So each of these points here corresponds to like an observation of an individual supernova. So across all of the yellow points, across all of the red points, across all of the purple points, we're looking at dozens of different supernovae, all in different bands. So all of the yellow points are lots of different supernovae that are at roughly that 0.21 redshift. We know all of their redshifts a lot more precisely than that roughly 0.21, and that's how we scaled them in the model.
So it wasn't scaled by the band, but by the actual photometric redshift of the point.
Actually, spectroscopic redshift, because we have spectroscopic redshifts of the host galaxies.
So this is kind of like a stacked light curve that we've made for an individual redshift, right? So if we go and do that for all of the redshifts for all of the DES supernovae.
When you say stacked light curve for an individual redshift, do you mean individual intrinsic color?
Yes, essentially. So back at this plot here, you can see that all of those black dots in the middle of the curve are lined up roughly on the x-axis at point like 448-ish. So if we're thinking about, if we want to measure the width of an individual supernova at redshift 0.48, we can compare its photometry with this stacked light curve. So yeah, when we go and do this for all of the possible redshifts for all of the DES supernovae, we get this. The y-axis here is the vertical dispersion for each of those different plots, except we're now doing this roughly 1,500 times. And you can see that for lots of different values of B, we actually get a minimum in this flux dispersion corresponding to B equals 1, more or less. So I've pointed out two specific B values here, B equals 1, which is kind of like our best fit for this time dilation. And I've also pointed out B equals 0. So if you think about the previous model, 1 plus z to the power of b, if we have b equals 0, that essentially will give you 1 plus z to the power of 0, which is just 1, which means we're essentially not scaling these in time at all. So that would correspond to no time dilation. So you can see that b equals 1 being a lot lower than b equals 0 essentially is good evidence that we actually see time dilation. And it's a very kind of model independent way of getting there.
What is the line representing rather than just an X? Is it the uncertainty in the measured flux dispersion?
Yeah, across the 1,500 DES supernovae. So each different kind of stacked light curve we get will have a different flux dispersion here. So the uncertainty, like the error bars in this, corresponds to like the different flux dispersions we get when we look at different stacked light curves, essentially. Once we've gotten this, we can make these stacked light curves for all of our DES supernova redshifts, and we can start comparing individual supernova light curves to these kind of stacked reference light curves. So here in the blue points, we have the photometry of an individual light curve. And if we kind of scale that to best fit this reference light curve, we can get a measure of the width of that individual light curve we're looking at. So given that we have roughly 1,500 type 1a supernovae, we can do this for all of them, making this stacked reference light curve unique for each of them. And we can get a measure of the width of all of the light curves so we can see how the width changes with redshift. When we go and do that for all of them, we get this, which is essentially the second main result in our paper. So you can see that on the x-axis, we've got redshift. On the y-axis, we have the width. So that's how much we're scaling it by. That's how much we're dividing the time axis when we're fitting these light curves. You can see that as we get to a higher redshift, we get proportionally higher width. And what we get here is you can see that a width corresponding to 2 essentially means that the light curve is evolving over double the time that we'd expect. And we see that roughly at redshift 1, which is what we'd expect. Our best fit of this, you can see, is the blue dashed line here, which is 1 plus z to the power of 1.003, which is extremely close to what we'd expect from cosmological time dilation with our models.
So this 1.003 plus or minus 0.005, that's like your measurement of B. So if we went back to that kind of one where you had the dispersion as a function of B, or like the minimum dispersion as a function of E. So you've measured B to be 1.003 plus or minus 0.005. That's a very high significance detection away from zero. It didn't seem from that plot that it should be this. I was expecting like 1.1 plus or minus 0.1 or something.
There are two different measurements. One's the crudest possible, no model, just reduce the scatter. And here we've used the reference light curve to scale every individual supernova to figure out how much each individual supernova has been time dilated and put it on this plot. So that's what we're seeing.
So what we were doing before, where we were just minimizing the flux dispersion, that was essentially like the most model independent way of getting time dilation that at least I've seen in the literature. Maybe there's another paper that's done it a bit better than that, but not that I've seen. But essentially, this like precise B result here relies on us already minimizing the flux in this reference stacked light curve. So this kind of has the additional assumption that we need to minimize it first, whereas when we did this, we're actually doing that to get the time dilation result, if that makes sense. So this has kind of one extra little assumption compared to before, but it allows us to get like an actual numerical value of B. One really key thing about this that I haven't seen in a previous paper where they found cosmological time dilation in supernova light curves is this is kind of band independent, whereas before they could only really get this in individual bands. So this plot here, each point is colored according to how many bands we're actually getting that measurement in. But there is another plot in the paper where we do this for each individual band. This is just kind of the combined results of those.
Hi, everyone. We realized after recording that Ryan and Tamara hadn't really quite gone into details about exactly why one expects this B parameter to be 1, why one expects the time dilation to scale as 1 plus Z. So Ryan and I are back in the studio to do a quick update on that. So Ryan, do you want to tell us briefly why B should be 1?
Yeah, so there are several different derivations you can do for why we actually expect time dilation. So you can do kind of like a general Newtonian case, a special relativistic case, or a general relativistic case. And I've picked out kind of the simplest derivation you can do that shows why we expect time dilation. So in the top equation here, this is nothing really controversial. This is our kind of definition of redshift. So you can see that our redshift parameter Z depends on the intrinsic emitted frequency of light that we observe minus the observed frequency of the same light divided by that observed frequency as well. So you can simplify that fraction a little bit and get the emitted frequency over the observed frequency minus 1. Move that 1 to the other side, and you get that second equation there. So that's the first time you kind of get that 1 plus Z. And that just depends on the intrinsic emitted frequency over the observed frequency. And given that light is a wave, you expect it to kind of like cycle over time. And so if we're looking at the same intrinsic light, we would expect that even if it's kind of like changed color from our perspective, it should still have kind of like the same number of cycles per unit time. So you can see here that in this third equation, we show that the emitted frequency is kind of like that number of cycles per time when it was emitted. And the observed frequency is the same number of cycles, because it's the same intrinsic light, per time in our coordinate frame, so in our observed time. And so since this is the same light, if you take a look at the fourth equation here, since it's the same light, those counts, the number of times it cycles per unit time, they're the same. So they actually just cancel out in this fraction. And so that means we get delta time in our observed frame, in our like observer frame, divided by the delta time in the emitted frame. So in the rest frame of the supernova or whatever transient object you're looking at.
So this delta TE here, if we remember, is the time between, I guess, the start of the light curve and the end of the light curve. So this count is the number of wavelengths in that full delta TE period of time. And yeah, as you said, it has to be the same because it's it's the same light. If it was different, you'd be able to like get together afterwards and say, hey, I emitted 15 wavelengths. How many did you measure? Well, I measured 16. And then that's just like, that's not consistent with reality. So it has to be the same number of counts. Yeah, cool.
Yeah, that's one way of looking at it. The key thing here is that kind of like the two key things here is that we're looking at the same kind of intrinsic color of light, so that kind of count parameter stays the same, and also that the speed of light is constant. But yeah, essentially, since we're looking at the same intrinsic color of light, which has changed color in our observer frame, we can cancel those counts out in the fourth equation there, and we get that delta t in the observer frame divided by delta t in the rest frame, the emitted frame. And so remembering that, like, if you work your way up, you can see that this is still equal to 1 plus z. So you can just move the delta t to kind of like the other side of the equality there, and you get delta t observed equals 1 plus z times delta t emitted. And so that's why we expect time dilation.
Yeah, in our email exchange, you, me, and Tamara, this was described as simple, and I guess mathematically, I totally agree that this is a very straightforward thing. I'm just going to quickly give my feeling for the simplest kind of intuitive way of this. So, and it's mathematically equivalent. It's just like a different way of describing the same thing. It's more in terms of distances rather than frequencies. But the start of the light curve was emitted at time t equals 0, and then the end of the light curve was emitted delta TE later, as far as the supernova itself is concerned. And so that kind of, those two light rays or photons travel away from the supernova and towards us. And at the beginning, they will have a separation, some delta x, that is whatever the speed of light is times that time, right? Because the first one got a head start of delta t, and so it's speed of light times delta t ahead. Now, in an expanding universe, in the co-moving coordinate system, the emitter and receiver are kind of stationary, but the space is expanding. So as those two light rays travel from the supernova to us, the distance, this delta x being c times delta te, has stretched by the ratio of the scale factor at emission to today, which is again this nu e over nu naught, or 1 plus z value. So therefore, the distance has stretched by 1 plus z by the time it gets to us. And if speed of light is again just c, if the distance is stretched, then the time it takes between the first bit of the light curve getting us and the last bit of the light curve getting us has also stretched by 1 plus z. So it's, yeah, exactly the same kind of, if you just change frequencies to distances, the maths is more or less identical. And whichever thing is more intuitive to you, you can latch onto as your explanation. And yeah, I guess I'll put a link into the description to a reference from Ryan's paper that has the full GR and, as you said, SR and Newtonian physics derivations of these of this result.
So there is a lot of scatter in these points, of course, and at least some of that scatter is due to like noise in our data, but actually a good chunk of, if not most of this scatter is due to like intrinsic variation in the supernova light curves. So there's a very well-defined width luminosity relationship for type 1a supernovae. So brighter supernovae actually have wider light curves, and we don't correct for that in this paper. We just treat that as kind of noise, like scatter on this plot. And so one way that we can kind of visualize that is by comparing this scatter with the stretch parameter from the SALT3 light curve model. So stretch is essentially just how wide a supernova light curve intrinsically is. It behaves much the same way as time dilation does, like it broadens the light curve, but it's kind of like an intrinsic property. It's not due to the universe expanding, it's just that supernova itself is intrinsically, like its light curve is intrinsically wider.
And it doesn't depend on redshift, it depends on luminosity. Like it.
To some extent. Tamara will talk about that in the next slide. But essentially, yeah, we don't use this SALT3 stretch parameter, but this is a really good plot just as like a consistency check to show that the points that lie above our best fit, like the intrinsically wider curves, do correspond to a larger stretch from the SALT3 model. So yeah, this is just like a really good consistency check of our data to make sure we're doing like our method is actually good at what it's doing, essentially.
one of the concerns that people often come up with is that we know that there is some intrinsic width variation in supernovae. So how can you detangle that from the time dilation? And when we had a paper in 2008 with Stéphane Blondin where we used the spectra of supernovae as a clock rather than their light curves, because the spectra don't have this width variation effect. So it's like the depth of lines in the spectra over time and stuff can be used as a clock as well. But we did that with 13 supernovae and the error bars are large. So here we have enough supernovae at high redshift now that we don't really have to worry about this width luminosity relation, because the width in scatter is much smaller than the factor of 2 time dilation that we expect. So you've got a 10 or 20% variation in the width intrinsically, but you're looking at a factor of 2 time dilation over this light curve. So we are at the point where that can be just treated as noise and it's not biasing our signal.
Yeah, exactly. So when you say, people say, how do you disentangle it? Is the answer not just, again, this like 1 divided by square root of n? The more data you take, the data that shouldn't be correlated with the effect you're looking for should just wash out. And it doesn't seem like any reason why this wouldn't wash out.
Yeah. So the only reason that it might not wash out is if there was some variation in the population with redshift, for example. People have tried to measure whether there's any population drift, like whether the stretch of supernovae, the intrinsic width of supernovae, could change with redshift. And so this plot on the left is a model that was proposed where you expect people had measured maybe a stretch of a couple of percent change. So like the mean stretch might be a couple of percent different at low redshift compared to high redshift. We actually don't see that trend in the DES supernova data for whatever reason. But even if we did have such an amount of variation, it's only a couple of percent. And again, not a factor of 2. So in the bottom right plot here, you see the light curve width versus redshift plot, and the different lines show the time dilation you expect in black. And if you have a drift of a few percent in the stretch over that time, you would get the red line. So it's negligible difference compared to the horizontal solid line, which is no time dilation.
I guess there's also if you tried to ascribe, on a theoretical side, if you tried to ascribe the whole of this effect to some sort of redshift drift, there's the highly suspicious thing is like, why would the size of the signal directly correlate to like the size of the universe? Because what 1 plus z is the scale factor, is the size of the universe. So yeah, why is this supposedly astrophysical thing correlating so closely to that, which would be very weird.
Yeah, trying to explain this result by some sort of variation of supernova behavior over that redshift would be extremely contrived.
I guess this is something that is kind of uniquely nice to supernovae in that they do have this. Okay, maybe me from the outside, I don't know enough about supernova physics. Supernova astrophysicists might be rolling their eyes at what I'm about to say, but that you do expect them to be very consistent with redshift, because they explode when a certain condition happens, whether that condition is happening in the early universe or late universe. Whereas with galaxies, yes, you do actually expect early galaxies to be different to late galaxies, because there may or may not be as much gas floating around. But yeah, I guess then maybe the issue might just be the environment around the supernova when the light comes out might be different at early and late times. Is that perhaps the fear that?
Yeah, so there may be reasons people have speculated that supernovae might be slightly different at high and low redshift. Might be if you have you've got like these carbon, oxygen, white dwarfs, if you have a slightly different balance of carbon and oxygen, and so different metallicities and things in the progenitors could cause slight differences. But these are that could be causing some of this intrinsic variation that we see, but we don't see a ginormous drift over the redshifts that we're looking at in those properties. So that's one of the reasons supernovae are so nice.
So yeah, that top right plot there just shows like the stretch versus redshift in the DES supernova sample. So you can see that the stretch is actually quite like symmetric about that black kind of best fit line there. So like the stretch is very well sampled in both directions. So like stretched and kind of like squished, I guess, supernovae are very well sampled for essentially all of our redshifts.
Just asking a naive question, the same people who have said to Tamara in the past, how can you disentangle the time dilation from the stretch? How have you disentangled the stretch from the time dilation here? How is the stretch measured here?
That's actually an important thing. So the stretch here is model dependent. It's part of the SALT3 model for light curve fitting. The SALT3 model does assume time dilation in it. So the residuals in how wide the light curves are is naturally going to happen, that you're going to see this trend. If you flick back to the previous slide. Yeah, so this is really what you would expect because the SALT3 model has like residuals in width. Now, whether that correlates with the luminosity is something that would be separate, though. So that's not what you expect from just the time dilation part of things.
That does feel then that it is a little bit less persuasive that it's not correlating with redshift, because
the main point is from this plot that the scatter, all of the intrinsic variation in supernova light curves is smaller than the size of the slope that you need to explain time dilation. So if it was like a drift in population from the most narrow to the most wide supernovae over this redshift range, you still couldn't get a slope this steep.
You essentially get a scatter of about 0.15, so like roughly 15% from this, whereas the actual time dilation signal out to Z, like roughly 1, is like a factor of 100%.
So the most extreme selection effects that we could expect, or the most extreme drift of properties of supernovae across this redshift range, would give us, a 10% slope, not a 100% slope. So like a 0.1 instead of a doubling of the width.
I might be about to repeat exactly what you just said, but yeah, if I put everything, all of these data points just going through a horizontal line, and then I play the silly game of taking on the far left the lowest point and on the far right the top point, it's going to have a shallower slope than this. I see.
And yeah, we see no evidence of drift in the supernova population across our sample.
Yeah, so where to next with this? I guess you were skeptical at the beginning of the recording about how useful this might be for, cosmological constraints and things, but perhaps you could speculate on some things, or you in the audience. Like I'm sure there must be exotic cosmology models that would predict a different scaling of this, whether it's back reaction, perhaps inhomogeneities ruining the FIW metric, or modified gravity models where there's different metrics for light and for structure or whatever. I don't know. There must be something that's ruled out by this. It's so precise. But what else are you planning on trying to improve the result and using it for other stuff?
I mean, we can always have more data, I guess. So maybe there'll be a next survey coming along with another 1,000, 10,000, I don't know how many supernovae that you could like further constrain this a bit. Another thing to look at is finding time dilation in other objects, for example. So people have done it with gamma ray bursts before. One of the co-authors has actually done it with quasars as well. So further constraining time dilation in other transients would be really interesting as well. But essentially, like this just confirms what we already kind of knew to begin with. So I guess you could make the argument that at least to some extent we're done, I guess. Yeah, but no, there's always more to do, I guess.
I'm satisfied with this, that time dilation has been measured and we don't have to question whether that's there anymore. So to some extent, that's wrapped up and done, I think, with this. There's cool things that happen alongside time dilation. So if we're in a local overdensity or underdensity, you can also get gravitational redshifts, and those can affect our measurements of Hubble constant and stuff. We expect that to be a very, very small effect. But if you have peculiar velocities and things like that, maybe we can use some time dilation to disentangle peculiar velocities from expansion velocities or something like that in the future. That would be potentially interesting.
The thing that this feels the closest equivalent to is like in terms of, yeah, okay, everyone expected it to be this, but great, it's been done, would be, I guess, with the first gravitational wave detection of colliding black holes, where they also got the optical follow-up, which proved that the speed of gravity and the speed of light was the same because they arrived at the same time. And okay, well, congratulations. But there were a huge number of modified gravity theories that were just obliterated in one go because of the precision, because it was so far away. Arriving at the same time means the speeds must be close to, 1 part in 10 to the something ridiculous, like a 5 or more. So this feels kind of similar, that there must be some class of modified gravity or something models that have just been shelved, but maybe not. I don't know.
Yeah, no, that I think that's true. There is models. Tired light's the one that comes up that I get emails about most often. That doesn't work with this. Doesn't predict time dilation.
Yeah, but I was thinking other ones that might not have already been ruled out by other stuff. I don't know.
Yeah, I'm not sure. If someone knows, let me know. And of course, gravitational waves are also something that display time dilation, and that's assumed and measured in their analyses of the gravitational wave signals.
So what work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the community?
Maybe I am a little bit biased, but I'm really interested in the in merging like binary black holes, in particular them merging around AGN. And I'm also working on something to do with that, so I am a bit biased, but I think it is really interesting in how people are like kind of constraining these gravitational wave signals from where, like what kind of environments they're coming from. And I think that little black holes merging around like a really big black hole, I just think that's pretty interesting.
I wasn't aware that those observations were being successfully made. I know that obviously binary black hole mergers are being detected, but the around the bigger one, I wasn't.
So it's not like conclusively shown, but based on like simulations and models about what it would look like around AGN, it's at least a bit convincing, at least to me.
Thanks everyone for watching. That's the end of all the dark energy supernova talks for now. If you haven't seen them all, then you should go check out the ones you missed. They're all awesome in their own way, whether you're into beyond ΛCDM, tensions, the data itself, or new detections of subtle cosmological effects. There's something for you. Otherwise, the channel isn't actually called Supernova Talks, so if you're new to Cosmology Talks, there's lots of other goodness to explore from the rest of cosmology. Have a great rest of your day, and thanks, Ryan and Tamara, for the great talk.
Thank you.
Thanks.